Learn like a pro.
Welcome to The Explainer. Today, we're going to turn some pretty complex physics into simple, intuitive drawings. I'm going to show you how you can map out pretty much any physical force problem and find the answer, not with a bunch of complicated math, but literally with just a ruler and a protractor. So let's get sketching. So here's our game plan. We're going to start with the absolute basics, the language of vectors. Then we'll learn the one single rule you need to combine them. After that, we'll look at the only two situations you will ever encounter. We'll solve a couple of real examples, and then we'll wrap it all up with a universal workflow that you can use on any problem that comes your way. All right, first things first. You know, every great blueprint is built from simple, repeatable parts. And the entire world of forces, our fundamental building block, is something called a vector. It's just a simple arrow, but it tells us everything we need to know. Think about it. Any force, whether it's gravity pulling you down or the tension in a rope or just a simple push, it really only has two key properties. How strong is it, and which way is it going? Well, a vector is the perfect elegant symbol to capture both of those ideas at once. Okay, and this is where the magic really happens. We get to translate this abstract physics stuff into simple geometry. All we have to do is decide on a scale, like say 1 centimeter on our page equals 5 newtons of force in the real world. Just like that, the arrow's length tells you its strength, and its angle tells you its exact direction. It's a perfect visual translation. So now that we have our building block, the vector, let's learn the single most important rule for putting them all together. Seriously, this is the secret sauce to adding forces together visually. This is called the head-to-tail method, and honestly, the best way to think about it is like a relay race for forces. The first runner, our first vector, finishes its leg of the race, and the second runner starts exactly where the first one left off. By chaining them together like this, tip to tail, we can visually add up their combined total effect. And the process? It is always the same. You draw your first force, making sure it's to scale. Then, right from the tip of that first arrow, you start drawing your second force. Then your third, and so on. The key here is that you're creating a continuous path that shows the journey an object would take if it followed each of these forces one after another. Okay, so now that we've got that technique down pat, we come to the central question. This question determines what kind of drawing we even need to make. This is the big fork in the road for every single force problem out there. Before you even pick up your pencil, you have to ask this one question. Is the system balanced? You know, is it staying still or maybe moving at a constant speed? Or is it accelerating because the forces are all out of whack? The answer to that question dictates the entire shape of your diagram. And get this, there are only two shapes your diagram can ever make. That's it. If the forces are perfectly balanced in a state we call equilibrium, your vector path will form a perfect closed loop. It'll end exactly where it started. But if they're unbalanced, in non-equilibrium, you're going to be left with a gap. You have got to remember this. A closed loop means the net force is zero. Simple. Everything cancels out. That open gap, though, that gap is the leftover force. We call it the resultant force, and it represents the overall change in motion. So that gap isn't a mistake. The gap is the answer. Okay, let's tackle our first case study, equilibrium. We know the object isn't accelerating, right? So all the forces must add up to zero. That means our mission, should we choose to accept it, is to find the unknown force by drawing the one vector that perfectly closes the loop. So the goal here is super simple. You draw the forces you already know, one after another following that head-to-tail rule. And because you know the system is in equilibrium, you also know the shape has to close. So the missing link that you draw to get right back to the start, that's it. That's your answer. That's the unknown force. Here's a real-world example. We start by drawing the 7 Newton weight vector, pointing straight down. Then, from the head of that vector, we draw the 8 Newton tension vector up at its 30-degree angle. The missing vector that gets us back home, back to our starting point, represents that unknown force F. We just measure its length, use our scale, and boom, we find it's 4 newtons. Now, this is really cool. For symmetrical problems like this hanging weight, there's a fantastic shortcut. First, draw the one force you know, that 20 Newton load. Then, from its head and from its tail, you just extend lines out at the given angles for those unknown tension forces. And where those lines cross, that's your solution. It perfectly defines the lengths and therefore the strengths of the two tension vectors. All right, so now let's see what happens when the forces are unbalanced, when our drawing doesn't close up on its own. Remember, that open gap isn't a mistake. It's actually the answer we're looking for. When your chain of vectors leaves you with a gap, That gap represents the net outcome of all the forces combined. It's the overall push or pull on that object. We call it the resultant force, and it's simply the most direct path. Think of it as a shortcut, from your starting point all the way to your ending point. So in this example, we've got 3 different forces all pulling on an object. What do? We just chain them up, head to tail, one after the other. The direct path from our origin point all the way to that final arrowhead, that's the resultant. We just measure its length and its angle to find the net effect, a single force of 20 newtons acting at 48 degrees. Easy. Okay, we've covered the components, we've learned the one big rule, and we've looked at the 2 scenarios. Now let's pull it all together into one master plan that you can apply to literally any problem involving forces. And here it is, the master plan. It all hinges on that one question. Are the forces balanced? If the answer is yes, you have an equilibrium problem. Your goal is to find the missing vector that closes the loop. If the answer is no, it's a non-equilibrium problem. Your goal is to draw the resultant vector that bridges the gap. That is it. Every single problem is one of those 2 missions. So let's just boil this all down. The really big idea here is that forces have a shape. By translating forces into vectors and just arranging them head to tail, you transform what looks like a complex physics problem into a simple geometry puzzle. Your ruler and protractor literally become your calculator. And this isn't just theory. This is a new way of seeing the invisible world of forces that's all around you. So next time you see a leaning ladder or a hanging sign or someone pulling a suitcase, you now have the mental blueprint to actually sketch out those forces. You can see what other people can't. So what are you going to analyze first?